Alright everyone, in this video we're going to continue our example, and in the previous video what we did is that we found the governing equations for this system. I'm just going to write it out. Governing equations. We can do this on the fly, it's pretty easy. So we had a mass matrix or inertia matrix, which was this. Now I'm doing it as I go, simply because the method that I showed you before is that fast, and we're going to write the damping matrix. Well, actually there are no damping matrices, so we're just going to write the stiffness matrix, and we're going to have K1 plus K2 here minus K2. It's symmetrical, so that's easy, and we only have K2 here. Theta 2, and all of that is equal to the null vector dimensions 2 by 1, because there are no external forces acting on the system. The second step was to find the eigenvalues by solving the determinant of the stiffness matrix minus the eigenvalue times the mass matrix or inertia matrix, setting that is equal to 0. And then number 3 is that the ith natural frequency is equal to the ith eigenvalue. Alright, so the results that we found are parametric. They are functions of the stiffness and the inertia of the second disk. Now, in order to find the mode shapes, we're going to solve this equation. Now, this guy is what used to be inside here, but then we multiply it with what's called an eigenvector. And remember that last time in the other example that we did, we used something that had the form p sub 1, p sub 2 for both of the eigenvectors, but we always sort of normalized it, divided by all the terms by the value of the first term, and we always ended up with something like 1 and some constant. So what we're actually going to do is simply right off the bat say that the eigenvectors have this form over here, and what you're going to find out is that it's going to simplify the notation, and it's also going to simplify the calculation. Alright, also last time we found that the inertia matrix was this guy and the stiffness matrix was this guy over here. Alright, so we go through the first one. Now I decided to transform this equation and replace the eigenvalue by the square of the natural frequency, and that again is because the ith natural frequency is equal to the ith eigenvalue, therefore, which means that it's equal to this, and so we end up with this one over here. The reason I want to do this really is that since I use a calculator that can solve these types of equations, then I don't want to have the extra step of having to take the square root of that value. At any rate, we take the first natural frequency squared, which we found to be, well, actually this guy over here, multiplied by the inertia matrix times the first eigenvector, and if you do the multiplication, you're going to end up with first equation and a second equation. And so you have equation number 1 here, equation number 2 here. They should give the same value when you solve for R1. What you'll find is that they might be exactly the same depending on how many decimals you keep, but they also might be slightly different. In this case, the difference between the two are simply due to round off errors. So we're going to say that they're close enough. If you have a 10% difference between the two, then that's not acceptable. But as you can see here, we have less than that. Actually, there's a small mistake here. You should see a 3. All right. Okay, so we're going to take the average. We're going to say that R1 is equal to a half times 1.3031 plus 1.3026, and that is equal to 1.3029, which is this over here. All right, so we actually already have our first eigenvector. We repeat the same process. This is the stiffness matrix. This is the second natural frequency squared. This is the inertia matrix. And this guy over here is the second eigenvector. Now we substitute with the values that we know, and we expand this this term over here. We're left with this matrix. And then what we do is that we will get, again, one equation, two equations, which I wrote here. And again, these guys will say that they're close enough. And we want to increase our chances of, or increase our precision rather, by taking the average value, because we don't know if the first one is closer to the true value than the second one. So we're just going to assume that the average of the two is better. All right, so we said that R1 was equal to 1.3029 and R2 is minus 2.3017. So we can go ahead and write our two eigenvectors. We have two eigenvectors, which are also called the mode shapes. And the reason why we have two of them, again, is because we have a 2 degree of freedom system. So that's it for this video. If you want to have this worksheet as a PDF, then I've posted a link in the description below. Thanks for watching.